Okay. Hi. In this lecture, we are continuing our discussion on fluid dynamics. Uh, Last time we discussed the continuity equation in a very generalized form, and then we discussed Euler's equation, which describes the motion of a fluid. Today, what we'll do is we'll look at conservation of energy as applied to a fluid. Now, in your 11th and 12th standard, you have already seen an equation which talks about conservation of energy in the case of a fluid, and that is called Bernoulli's equation. So, we are going to rewrite this in a slightly more general fashion. So, we won't have all of the assumptions of an ideal fluid that we talked about before, some of them will be relaxed, and we'll see how we get a more general form of this old familiar equation. So the way to do it is to start with Euler's equation that we derived last time. Let me write down Euler's equation. It says rho times rate of change of the velocity is given by the body force Fb minus gradient of B. Remember, this body force is any external force that might be acting on your fluid per unit volume. So it's like a force density. So, so in fact, later in this proof, we will put Fb to be the force of gravity. So gravity being an external force. External, I mean, there is always pressure acting on the fluid. But if there's something else, like for example gravity, then that we are going to include inside this term Fb. What we'll do now is take a dot product of this equation with the velocity vector. So I get rho v dot dv by dt is fb dot v minus v dot gradient of pressure. Now this thing over here on the left hand side, notice that this is just half d by dt of v square. Why is that? Because v square is just v dot v. So derivative of this is v times dv by dt plus dv by dt dot v. So this is just twice. So that's why half d by dt of v square. This is fb dot v minus v dot gradient of the pressure. What I can do is I can also multiply by the volume element delta v everywhere. So why don't I just do that in this step? Now rho delta v is just the small mass element. And if you remember, what we are always doing is whenever we are having some kind of flow, we always consider some mass element and follow it as it moves through. So this dm is a constant. So I can pull it inside the derivative. So I get half b by dt let's call this thing equation 1. Now on the right hand side, I have two terms. One is fb dot v, and one is so this term and this term. So I'm going to try and now evaluate these two separately. So first let's look at the second term. For that, I will consider this quantity. Derivative of P delta V. So this is dP by dt delta V plus P d by dt of delta V. Now over here I'm going to use two results that we derived last time. So instead of dP by dt, we know that this is the total derivative of any quantity is the sum of the partial derivative plus V dot gradient of P. And also d by dt of delta V is also something that we had derived last time, and this just turns out to be V dot no gradient divergence of V delta V. Correct. So these are both results that we had derived last time in the lecture. From this, what did I want? What is my second term? My second term is V dot gradient of pressure. Do I have it somewhere? I have it here. V dot gradient of pressure. So V dot gradient of pressure delta V is d by dt of this minus partial derivative delta V minus P divergence of velocity delta V. So we'll call this fellow equation 2. And the third thing that I'm interested in, the other thing that I'm interested in over here is this FB dot V. So we'll say that there is an external force acting on the system, and that is gravity. So FB delta V. See, FB is the force density, force per unit volume. So FB times delta V is just the force that is acting. So this is just delta M times G. And I'm going to write G vector to indicate the fact that there is a direction to it. It's acting in the downward direction. I hope this step is clear. Mass times, what I'm saying is force density multiplied by volume is just force. That's what I'm saying over here. So this is rho delta V, that's dm, times G. Now over here, it's convenient to write this G vector as, let me first write it and then I will explain to you what it means, what I have done. So I'm going to write this as rho delta V, gradient of a potential. Now what is this? Why have I written it like this? When we were discussing work and energy back towards the beginning of this course, we saw that if F is a conservative force, then I can write F as the gradient of potential energy. Correct? Now, if I'm talking about force per unit mass, which is essentially g vector, then this I should be able to write as gradient, negative gradient of u divided by mass. U is called over here potential energy. This is one way of defining it. So potential energy per unit mass, negative of that is called potential. So phi, which is called the gravitational potential, is minus potential energy per unit mass. To give you a feel for what exactly this means in terms of gravity, so potential energy for a gravitational for a point mass would be minus gmm over r. Potential would be, first of all, plus, because it's the negative of the potential energy, and per unit mass. So this is gm over r. So potential energy versus potential. It's just a quantity, just a definition of a quantity. So I'm writing g as gradient of this phi. Phi is a scalar quantity. So I'm taking gradient of it. Alright. So this is FB delta V. We were interested in the dot product of this with the velocity vector. So V dot FB delta V is rho delta V dot gradient of phi. But this V dot gradient of phi, again from what we had derived in the previous lecture, is the difference between total derivative and partial derivative. Basically it's this same rule. Total derivative is partial derivative plus V dot gradient. So same thing over here. I'm going to write this as total derivative minus partial derivative. So we'll call this equation 3. So if you notice, we had equation 1 on the right hand side of which we had two terms. And those two terms are exactly what we have derived in equation 2 and equation 3. So let's put 2 and 3 back in 1. I get half d by dt first term was fb dot v times delta v. Fb dot v times delta v is okay. And minus of this equation 2. So let's be careful with the signs because I have to take the negative of this. So minus d by dt of p delta v plus del p del t delta v plus p divergence of velocity delta v. Okay. Now there are a lot of total derivative terms. Let me collect all of them on the left hand side. plus P. And everything else I'm going to keep on the right hand side itself. Let's okay, this looks correct. Oh, sorry, why did I, this is row 5. Is this fine? Yes, this looks fine. Okay, so this is the equation that we wanted. Let's look at all of these terms one by one. Let's look at what's happening on the right hand side. So there is one term which is del P by del T, partial derivative of pressure with respect to time. What is this? This is time variation of pressure. See, earlier in your 12th standard, when you were discussing Bernoulli's theorem, you had some kind of a pipe, and the pressure difference on both sides was basically constant. You never talked about what happens if the pressure is changing with time. Now, since this is a generalization, this allows for the fact that the pressure might not be constant, it might be a function of time. So, del P by del T tells you what is the time variation of pressure. Of course, if pressure is not going to change with time, then this term becomes 0. So, in your old Bernoulli's equation, this term is not there. Second term over here is, there is one term which involves d phi by dt. This is the time variation of the gravitational field. Or gravitational potential. Once again, in most cases, in most normal cases that I can think of, gravitational potential is not going to change as a function of time. But of course, if you're talking about some exotic phenomena, like for example, maybe you're talking about, so when you're studying the internal structure of a star is basically a sphere of very hot gases. And these gases are moving around, so there is a lot of fluid motion happening inside the body of a star. So over there, it's possible that the gravitational potential might change with time. Or if you're thinking about some kind of astrophysical phenomenon like a supernova explosion, so over there the gravitational potential can change with time. So in all such kinds of exotic phenomena, you can have a time variation of the gravitational potential. Here on Earth, I can't think of any reason why the gravitational potential might change with time. But anyway, so this is one more generalization of Bernoulli's theorem. This equation works also if you're talking about a varying gravitational field. There's a third term on the right hand side, and that involves gradient of V, divergence of V. Now, what is divergence of V? We had seen this last time. Divergence of V tells you whether a fluid is compressible or incompressible. So, if this is non-zero, then that means the fluid is compressible. So earlier you were always discussing incompressible fluids, but now because this term is there on the right hand side, it allows you to also describe what is happening if your fluid is compressible. So that's why this is a generalization of Bernoulli's theorem. On the LHS, what are the terms we have? We have half rho v square delta v. This is just the kinetic energy of the fluid element, because rho delta v is the mass of that element, delta m. What is P? P is the pressure that you have applied. And what is rho phi? Uh, Rho phi delta V, let's call it. Well, since we are putting delta V everywhere, I will call this potential energy due to the applied pressure. And this is just gravitational potential energy. Because this is dm times phi. But phi is just dm times gm by r. So this is your gravitational potential energy, gmm by r. Well, minus. Or if you're talking in terms of the old Bernoulli's equation that you're familiar with, this is like your rho gh term, rho gh, but also with the delta v. So your old Bernoulli's equation was just the left hand side. See, left hand side says d by dt of these three terms. And according to your old Bernoulli's theorem, right hand side was 0, because there is no time variation of pressure, there is no time variation of gravitational field, and your fluid is incompressible. So if right hand side is 0, then d by dt of left hand side is 0, means that that left hand side, whatever is inside the bracket, has to be constant. And that is your old Bernoulli's theorem. So what we have written over here, this is the general form of Bernoulli's equation.